So in the Enjoying Math YouTube channel, so as the complex analysis graduate class in at Texas State University, so I already for a long time ago, I already launched Riemann's complex analysis like the course in a way to discuss with each of the individual participants. So we first like to have focus on learning how to compute the integral of differential forms, especially specializing in winding form and the area form. And do our computation was over either S2 or CP1 or the torus. And then we move on to the like the cohomological language to understand Gauss-Bonnet as a and we'd like to apply that as a concrete like the contents for getting the intuition inspiration for Riemann rule theorem so that so in this like the group of the study we have even spent more than I think around a year to understand the Riemann rule not in a just a logical way but to really figure it out how Riemann like the thought about came up with this kind of the original idea coming from the elliptic like the integral what's the meaning of the like the holomorphic one form in this like the context of Riemann surface theory and so on. So the purpose of today's like the conversation is eventually try to bridge from the like the participants here from Enjoying Math YouTube channel to the like the graduate students learning complex analysis at Texas State so that we can make the language exchange. Probably there should be the sum of our interest like K culture as well, and also math exchange so that we can more actively making the conversation to the contents that we are all definitely interested in. So today's like the conversation should be made in a way that each of the participant, you don't need to really introduce yourself if you don't want to, but you can just directly, it's just a suggestion, it's completely up to you that whether or not you introduce yourself or whatsoever, so that we can directly jump into like the math contents that we'd like to drill together. So, and you can also share your own thoughts, inspiration, and your own like the way of the thinking regarding the contents of the Riemann surface theory. And then I will give some like the at least brief like a comment on it, and we'll just go turn by turn. And that's for this like the record like the video. So I'd like to start from the leader of this team, Junhyuk, to go over your own thought, and let's just do it. And after I give the comment, so that the next one who can volunteer to speak, you can naturally just the raise your hand and you can go over your own like the like the part of the conversation. Okay, yeah, Junior, it's your turn.
어, 그냥 준비한 걸 읽으면 되는 건가요? 어, 네, hello. My name is Junhyuk. Uh, okay. Uh, I agree that in order to understand why a compact Riemann surface is an algebraic curve, one needs to understand line boundaries, divisors, and invertible shapes. But why I do want to learn this because the fact itself is important. I'm also puzzled by something else. Riemann himself didn't know this fact. So how on earth did he discover something like this in the first place? What kind of calculations or observations would lead someone to this idea? Was it because elliptic integrals involve polynomials, so he tried to relate them? Is that really enough to build this entire framework? Do you just compute elliptic integrals and somehow see the structure emerge? As for divisors, I can somewhat accept them from the perspective of winding forms. But line bundles, I really don't understand them. Why would anyone even think to collect such objects? And then taking tensor products gives a group structure. I honestly have no idea what kind of a leap of thought that is. Also, I feel like I've done quite a bit of computation on CP1. but I still don't really understand it. And now I don't even know what I'm supposed to compute on CP1 anymore. It feels like I'm running out of things to explore, so maybe I should move on to the Taurus. But I don't even understand CP1. So how am I supposed to handle the Taurus? This sort of feels way too difficult. Thank you.
Yeah, so this is very important, like the question, including the valid, like the several, like the valid, like the perspectives. So, I first wanna point out that the observation that definitely Riemann was able to find was the starting from two primary, like the holomorphic functions that we knew it must be multi-valued. One is, as you all know, y equals square root of x. And if we complexify it, we know, so this is multi-valued, so that this gives the natural, like the bridge to the CP1 or the two-dimensional, real two-dimensional sphere. But this was really just coming from nothing but the zero set of the polynomial y squared equals x. So that we rather start from the zero set of the polynomial, and when we try to adopt to the complex analytic point of view, so that this naturally brings the Cauchy's complex analysis, and it's also the same for y equals square root of the cubic polynomial with each of the distinct, like the three zeros, so that again we just already start from the zero set of the polynomial, and then we adopt to the Riemann surface perspective, and the multi-value, like the nature, is now transferred to understand the covering map, like the language to create this compact Riemann surface. In this case, as you all know, the case of the torus or the elliptic curve. So the observation is exactly opposite, not from the ignorance of knowing compact Riemann surface is an algebraic curve. We already start from the algebraic curve, and then we just deduce the corresponding structure. The space structure should be the compact Riemann surface via the more like the covering, like the perspective, or the like the branched covering. This is supernatural. And when it comes to start from these types of the multi-valued functions with the square root, this is what I'd like to say. And the desire, so from the calculus point of view, is that so rather than using the integration of the differential forms over real. So the key desire to replace the field from real to complex must be nothing but applying the benefit pros of the Cauchy integral theorem of holomorphic functions. So that's the like the key, like the feature of rather than just looking at the gradient vector. Once we start from the gradient vector field, if there's a loop, then we know it should be zero by fundamental calculus. But we can completely just translate in terms of the Cauchy integral theorem. So naturally, the holomorphic structure play a role rather than talking about the integral of the vector field. Now still we have just a scalar value like the function with having the same like the key feature, and not just the case of the gradient vector field. We know the Cauchy-Riemann equation is equivalent so-called the curve-free condition, and that should be used to like the continuously deform the area that we'd like to take the loop integral, right? So that it naturally brings not just the gradient but also related to the like curve-free condition. So cohomology also play some role behind, and also you know from the experience of computing the Gauss-Bonnet type computation over CP1, you also know it's related to divergence as well. Even though this is not easy to see in the first place, but that's also like they also related. So so when it comes to like the adopt to the calculus over C, then we will almost automatically encounter topological obstruction. That is, there because of the open mapping feature of the holomorphic function. If we start from the like the, just the open ball, and the image of the via the non-constant holomorphic map must be open, and because of that, when we like create Riemann surface, especially compact Riemann surfaces, then the holomorphic like the image must be open and compact at the same time. But we know the codomain of the holomorphic function is C1. That cannot be happen. So that we already know that there is no non-constant holomorphic function on the underlying any compact Riemann surfaces, so that it is very natural thereby when you look at the CP1 in a sense that rather than just treating the point of the infinity as an undefined point, we already regard the infinity as just nothing but the North Pole, or we can explicitly set 0 versus 1. So that why don't we just add additional point on the like the codomain, so that rather than talking about the holomorphic function towards C1, we just want to say holomorphic function towards the CP1, then this concept exactly coincide to the concept of the meromorphic function defined on the compact Riemann surface. This is supernatural. So that let me just talk about the like the way of the imagining in our own way. So that there should be by all means one can consider to adopt to the Cauchy's complex analysis, just prefer to do the calculus computation oversee with many reasons. And once we are the allowed to doing that, then we know that for compact Riemann surfaces for our like the purpose, because there's no holomorphic function, so that are not able to use it. So that it is very natural to extend the class of the holomorphic function, allowing the infinity at certain point. And this concept exactly allows the concept of the meromorphic function, and that's also naturally brings the concept of the Riemann rule theorem in the following sense. So that when we talk about the setting compared to the Gauss-Bonnet, Gauss-Bonnet only requires, of course, we can generalize Gauss-Bonnet in various like the reasons and various like the settings, but when we just talk about the like the compact, like the orientable, like the surface, so there's no consideration of the divisor. But the reason why we need to consider the divisor is that we want to prescribe the data of the order of the zeros and the order of the poles. And also by generalized Stokes theorem and the residue theorem, the compact Riemann surface that topological obstruction play a role for each of the meromorphic function in a way that total numbers of orders of the zeros must be exactly coincide with the total numbers of the poles. So when you talk about the compact Riemann surface, this cannot be avoided. So that we first need to like the prescribe the data of these orders of zeros and the poles, so that it very naturally brings to the concept of the divisor, so that we first like to collect the divisor. And the I think the primary like the important like the example of the like the divisor is just nothing but the just a single point p, 1 times p. P is any point on the compact Riemann surface. So that if you look at the statement of the Riemann rule theorem, then we know we need to talk about the so-called LD and ID. And if you just plug in D as just nothing but P, then LP is just nothing but the collection of the meromorphic functions on a compact Riemann surface, such that the principal divisor part plus P should be greater than equal to 0. And if you think about the meaning of it, that should be like the translated. And if you need to get used to it, you can just think about this just or just a definition itself. That means we are looking at the collection of meromorphic functions that has the pole at point P and most order 1 and most order. And that's the way to interpret this, like the condition of LOP. So that you can deduce that this like the LP, this becomes C vector space. This should be also tracked in the logical way, but one is able to track this as a C vector space. So this like the fact that LP, the dimension is at most 2 is the matter from the Riemann rule theorem in the following sense. So this can be found from the one of my note that I post on the like the that's like the website. That so the followings are equivalent. So if you start from the compact Riemann surface, which is homeomorphic to S2, it does not imply in general that such a like the compact Riemann surface must be biholomorphic to S2, because homeomorphism is much weaker than talking about the biholomorphism. If you already have the compact Riemann surface biholomorphic to S2, then it is automatically implies it must be homeomorphic to S2. But converse is highly non-trivial, and in general it should be false. That's not the case for the complex, like the torus, for example. If it is just a homeomorphic to torus, does not mean biholomorphic torus, because there are plenty of other types of the torus. But Riemann rule says that in fact they are equivalent. Namely, if the compact Riemann surface is homeomorphic to S2, then it must be biholomorphic to CP1. And the between in this like the statement, there's a one more statement that is LP, dimension of LP is precisely 2. This is one of the equivalent criterion that such a compact Riemann surface must be biholomorphic to CP1. So I recommend any of you to check this like apart. This is a very beautiful application of the Riemann rule. Why all of a sudden homeomorphism establishes the biholomorphism. And if you just get track of this like the detail, you can notice the following. So the isomorphism or biholomorphism of the CP1 just means the metamorphic function whose like the order of the some pole should be just a one. So it's really just a simple form of the Möbius transform. So one can just summarize what one can discover from Riemann rule theorem is that if one is able to find the Möbius transform type of the metamorphic function, that must be the biholomorphism, and the proof is based on the Riemann rule theorem. This is one important like the application of the understand the divisor and also the application of the Riemann rule. And that also forces that if we want to look investigate the other types of the metabolic functions, then we should like move on to the next like the possible spaces, including the torus. So that the key like the perspective, I just want to summarize this way. So when we treat compact Riemann surface of genus G as a complex manifold, not as a real orientable like the surface, then we should use metamorphic function rather than the holomorphic function. And in order to talk about the metamorphic function, then we should get the data of zeros and poles with the orders of them. Then to describe them, it is so natural to like to fix the concept of the divisor, and divisor information via the Riemann rule tells us that so we can like classify as to from just a topological like the structure, for example. And so furthermore, what we might wonder is how do we able to use the information of the divisor to talk about the important like the implication of the Riemann surfaces. So now let me just go back to what you originally asked. So one of the question you ask is that how one was able to look at include Riemann, that why compact Riemann surface must be the algebraic curve, namely zero set of the single like a polynomial, how that can be made. So there are two like the key features for that. So number one, so the primary reason to consider the complex projective space is that so for the finite dimensional complex projective space, then we know from this the equivalent relation we can multiply by the least like the common divisor, right? We can multiply least like the LCM basically. Then we can kill the effect of the denominator because if we just treat the element in this like a CPN, then we can always like remove by multiplying any like the non-zero lambda, so that we can take the lambda to be LCM. That doesn't matter. So that the key argument is that if one is able to embed the given compact Riemann surface to the CPN, then it's over. That actually gives the proof. Then in order to do it, we should find the each of the like the components to fill this like the n tuple. Then that should be that treated as a metamorphic function. And in order to find such a like the metamorphic function, including the existence, then we need to find the divisor. So the structure of the machinery is that if we are able to find the divisor from the Riemann rule, that guarantees the existence of certain metamorphic functions, then that should be the candidate to embed this compact Riemann surface to like the CPN. Then that gives the algebraic relation. That's the desired like the algebraic relation of the algebraic curve. That's the like the structure. So the Riemann rule is just nothing but controlling metamorphic functions and metamorphic form. And one also primary usage of the Riemann rule is that if you take divisor to be just a zero, for example, then L of zero is just nothing but just a collection of just constant in that case because this is a collection of the harmonic functions. So the I of like zero, you can see that that becomes the collection of the holomorphic one form because there is no like a pole. If you just compare this like the data with the definition, then you can check the dimension of the collection of the holomorphic one form. I mean, this dimension means the as just a vector space. So this is exactly genus. So that the numbers of the holomorphic one form, we can exactly find how many they are. And So this is a little bit like tricky in terms of learning the proof for the students in a sense that so the one of the application of the Riemann rule is the counting exactly numbers of independent holomorphic one form. Whereas if you really try to prove the Riemann rule by yourself, actually need this like the fact. So it's kind of like the going around so that in order to really prove it, so what I did is I used the so-called the Riemann-Schurich theorem to establish this part of the genus equals the numbers of independent holomorphic one form. And by using that, then one should be able to prove this Riemann rule. And Riemann rule particularly just implies the numbers of the holomorphic one form. And we just want to look at the torus case to just establish just a one like the such a like the one form. And how do we find such a like the one form? Like this is like the last like the comment that regarding your like the thoughts and inspiration. So when we want to look at the metamorphic functions on the torus, then so this is one of the theorem of the biostress that so I think all of you definitely saw this like the several times at this point that the metamorphic function field over the torus is generated by two generators from P and P prime, where this P is a biostress P function, right? Elliptic P function. So that if you just compare P and P prime, it's very natural that the dP equals P prime times dz, where dz is a desired holomorphic one form because we know there's only one such a holomorphic one form up to the scaling, so that dz should be nothing but dp over p prime. So that what we want to handle of like the holomorphic one from dz on the compact like the torus complex like the torus is thus nothing but dp over p prime. If you try to write this out, this exactly match with the elliptic integral. And if you just take the integral of this guy, that gives the inverse of the like the bioslicer p function, so that now we are able to handle the elliptic integral. Even we definitely cannot find the antiderivative, so this was the entire like the purpose of the Riemann theory that rather than like the attacking the problem of the elliptic integral by just finding some like the clever use substitution or some like the different like the idea of something else. So he just complexify elliptic integral, and what he discovered is that this elliptic integral can be seen as a dp over p prime and then taking the integral. And we can do this because this can be translated as just something but holomorphic one form dz. Then if we just achieve the holomorphic one form, then we can talk about the well-definedness of the line integral for any path. Then we are able to take this integral that gives the answer of the elliptic integral. And in order to do it, we need to create the Riemann surface, and we want to complexify, and we need to check whether or not this becomes a not metamorphic one form but the holomorphic one form. But in order to do it, we need to know the information of metamorphic function and the metamorphic form. That's the key information of the Riemann rule theorem. So I can simply just summarize like this, so that we want to prescribe the data of the metamorphic function and the metamorphic form via the Riemann rule theorem. And this is a key feature of this Riemann surface theory. And we just definitely regard that now re-obtain as long as we have a control of the all metamorphic functions for each of the divisors, then we are able to also find the embedding. So just that's the story. I'm a little bit like the way around, I know it, but yeah, so let's understand it. So anyone can ask next like the questions or share any of your thoughts.
For next, I'm gonna share my status and thoughts about the studying the Riemann Riemann's complex analysis. Actually, I, I'm I'm thinking about the relationship between among the holomorphic line bundles, immutable shift, and the galactic divisor. Actually, the professor already gave me the relationship among those things, but I didn't get it about how the one can imply the other two stuff. Also, I just I just can write the definition about the divisor bundle and shape. with the support of the GPT. But after I start the discussion about how they are related, and GPT said me, you can read this note, but it actually brings some additional knowledge that I'm actually not familiar with. So what I want to talk about is that um, I should read that additional knowledge or the direction, but I didn't have a time or the energy to cover them. So I don't have a big question, but uh, my status is that I need to open these notes and gonna read them.
So here is the few comments regarding your curiosity related to the correspondence between divisor, line bundle, and also the shift. So I want to explain this way. So there are two like a different like the perspective to talk about this correspondence. Number one, so we are talking about the math. What I mean is that as long as we are able to establish logically correspondence, that's what it is. So even we might not have a good intuition about it, so as long as we are able to establish some correspondence, they could be useful first of all, as long as logically we are able to do it. But at the same time, the one of the like the reason to like the use those concepts must be coming from the how useful each of the concepts must be, either from the application perspective or at least the philosophical perspective. And I want to like to put emphasis, we should pursue both of them. Why philosophically it seems like or intuitively important, and what could be the like the really like the realistic like the usage of those of each of the like the mathematical like, objects. Those should be separately treated. Even we know though there should be correspondence. For example, so we are now super familiar with the using the equivalent like the relation. For example, we cannot even explain how useful they should be as long as you are a math major, right? But we also time to time change the perspective via the partition, and we just want to really like the use for each of the like the different like the definitions because they share their own like the each of the like the own feature, and that could be useful in some of the context in a very like the different way. So I'd like to say, so we first I'm not talking about I don't want to talk about the logical way of the establish the correspondence, but I want to talk about the philosophical part and the potential like the usage of these like the concepts for each. So first like the divisor. Divisor describes the numbers of the finitely many points with the data of the order of the either zero or the pose. That's what we know. So as that data suggests, that only tells us the data of the zeros and the pose with the order. Just that's it. And the Riemann rule says then we'd like to collect the corresponding like the information of the matter of either matter of functions or matter of poles. It's a matter of like the one form. It kind of makes sense that so that we because we are not talking about the holomorphic function, holomorphic one form solo, so that we should like to talk about the poles and zeros and poles data should be recorded somewhere, so that divisor kind of makes sense. So that's why the coefficient data is to be should be the integer like the value, so that if this is a non-negative integer or positive integer, it should be the order of zero. If this is a negative integer, then this is the order of the pole, so that it only concerns the data of the zeros and the pole with the pole with the order. So that's what the like the nature feature of the divisor. So now let's move on to the data of the line bundle. So I personally agree that line bundle, the wonder like the intuition should come from the either the tangent bundle or the cotangent bundle. I completely agree with that because those are the objects we feel completely familiar with it. But you might try to ask why we are feeling okay with either the vector fields or the differential form. One of the reasons that we want to use the bundle structure is because of the so-called local trivialization, so that even we do not know globally how it like the behaves something very weird, we don't care as long as we are able to find a very small like the open set from the base space, so that we can really view the open set of the bundle as a so-called a cylinder type open set. You understand what I'm talking about? So that as long as we view the same information via the bundle, line bundle, then we can really use this trivialization structure. So for example, so when you imagine either the vector field or differential form in your own way, you already treat, for example, the coefficient as a some reasonable function, right? So that for example, if you have a differential one form, then say dx, dy, dz, for example, you put some coefficient. And because we are not just talking about the covector, we are talking about differential form, you treat this like the coefficient as a function. That's the like the key feature of the section of the bundle. Then why you were able to like the treat like that? Because you already use the local trivialization. So that in that local trivialization, because independently for each of the point, it determines the coefficient. So that function times reasonable basis was coming from the local trivialization that does not hold globally. But you know it doesn't matter because as long as we know how to transfer from one to the other by or if we are able to glue them, it's kind of okay. That's the idea from like the, for example, CP1, you know how to transfer from dz to d omega by just multiplying some just a function, right? But we already adopt the perspective from the bundle structure, namely from the local trivialization, then this kind of explains why we need to adopt the like the line bundle. But there's a more like a context regarding it, just the not vector bundle or the line bundle is that as the definition suggests, line bundle means in the local trivialization, each fiber should be a vector space dimension one. So because of that, for each point, we can say it determines the value so that we can treat the section of holomorphic line bundle as a indeed holomorphic function. That also works for both of the metamorphic functions and also metamorphic form. So that as long as we start from the divisor, if divisor determines the corresponding line bundle, holomorphic line bundle, then locally it determines just a function, holomorphic function, which is we'd like to want to like to look at. And the perspective of the invertible shift is for gluing. So we know by the definition of the shape, it only cares whether or not we can glue them nicely in some like the unique way. And for example, partition unity play a role, and the holomorphic like the nature does not allow the partition unity. So that was the reason that we consider the cohomology. So that because we know the zeroth cohomology was talking about the global section information, but in general, the Schrodinger like the sequence of the shapes does not guarantee the Schrodinger sequence of the global sections. So that we should like in order to like guarantee the exactness, we need to look at the higher like the level of the cohomology. So that the shape like the data is concerned whether or not we can glue the local sections nicely, and if the failure should be measured from the higher cohomology. And also the one of the beauty of the like the Gauss-Bonnet and Riemann rule is that it's related to data of the from the H1 to H2 by just using this like the connected homomorphism coming from the so-called the first chunk class, which can be realized as actually differential 114. So it's also related to Gauss-Bonnet. So this is not hard to explain for the first place, right? So I just want to say that there are like the two like the key different like the perspective for this correspondence that concept of the divisor, concept of the bundle, line bundle, concept of the inverter shift, each of them has a different like the feature so that one can use their own like the benefit. Of course, each of them we should say pros and cons for sure, but as long as we can like apply this correspondence, then we can take the benefit. So for example, as a section, we might prefer to use the person from the line bundle. For gluing them, we might want to use the section in the ship. And the rigorous definition of the section from the ship and the section of the bundle are actually different because the ship does not allow the local trivialization perspective because ship itself does the definition does not contain such a like the consideration. But we know how to treat them, and in the at least level of the CP1 we know how to make the correspondence for each of the like the because the Picard group in this case or the collection of line bundle is just nothing but the initial like the set as you all know. So let me also give the like the one of the like the comment regarding one of the participants today. So why do we care the tensor product of the line bundle? I don't think that's the like the like the main focus for the question. So for example, so why do we treat the function composition as a like the group operation? Because we know that can be handy. That can be like the easy to handle as long as we have the perspective from group theory, right? So when we collect the divisors, then why do we wanna assume it admits the abelian group structure? Because if it has an abelian group structure, then we might be able to find the generator. Then once we find the generator, then we'd like to say we know everything. That should be the reason. So that the correspondence, we just do not want to establish a set correspondence, but we'd like to keep the structure that we can just reduce the information that we can just handle with just finite amount just object and data, so that abelian group structure should be considered. In that consideration, of course, you also know that the abelian group is like the corner consideration also gives the torus from the Jacobian of the variety. That's very different, important, like the idea behind. But basically, it's very natural to consider the abelian group structure first of all. Then, if we just transfer the data of the divisor to the data of the line bundles, then we want to adopt the same like the abelian group structure in the isomorphic sense, and that just gives a tensor product. Just that's it. So, for example, the tensor product in the algebraic geometry, like the word is used for like taking the intersection of algebraic varieties. But the tensor product is actually everywhere. It's not. It's kind of the question that why do we need to use the addition? Why do we need to define the multiplication? We are not able to answer that because it really depends on the context. And in this context of the tensor product of line bundles, is that because it corresponds to the abelian group structure of the divisors. Just that's it. And for the invertible, we can play the same game because the desire here is which structure and which and on which purpose we'd like to preserve. And as long as it just satisfies our own like the purpose, then we know we are able to use it because that's the way we use the logic. This is the answer I'd like to give. But the also way to practice for like the CP1 and the torus is that do still believe that the divisor, so one definitely need to establish this correspondence in a very explicit way on CP1 first. And then if one move to the torus, this is important. So divisor is to generate the important classes of the metamorphic functions and metamorphic one form. And for when it comes to talk about the torus, holomorphic one form definitely matters. And metamorphic function should be matter to embed to P2. And even P and biostatistical elliptic P function and P prime will be the generator of the metamorphic function field, but it's very like the desirable to find the divisor whose like the LD and RD ID correspond to this data of the P prime, DZ, this kind of thing. Because this is the reason to establish a Riemann theorem, so that you can just making the setting of the divisor for that. And this is actually the 10th note of my like the graduate like the class, so that this is actually the note I need to post very soon, but you're also able to find it very, very soon. And that's the next like comment. So yeah, please move on to the anyone who would like to keep asking.
Hi, my name is Song. Honestly, what frustrates me most in studying Riemann surfaces is the big gap between Riemann's original intuition and modern mathematical language. Example like the Riemann surface of square root g, or the torus coming from the square root of a cubic or quartic polynomial feel intuitive and well motivated, but I struggle to see how that intuition becomes the modern language of covering maps, ramification points, and branched covers. I feel something similar with line bundles. It is natural for me to think of them as generalizations of tangent and cotangent bundles, but I wonder whether it is okay to keep following the viewpoint that feels natural to me instead of trying to reconstruct Riemann's own way of thinking. Also, since I can only study this Riemann surface on weekends, I want to do meaningful computation on weekend, but I often don't know what exactly to compute, so I end up reading passively and losing interest. How do you deal with this gap between intuition and modern formalism?
There are actually so many important like the perspective like the behind. So first, I don't want to talk about the kind the type of the imposter syndrome in a sense that you might feel like the lazy or not sincere enough to prepare the study as the target of the either the computing or proving something seems unclear, and even just it's just hard to just keep this like the study more than a month this point to just keep the curiosity in a way that we can just like the preserving the pace of like learning or like the like grasping the like the inspiration. So that's already like the very like the impressive for all of the members here. I'd like to say this one. So first, this is hard math. This is difficult in general. So this is the mathematics of Riemann that connects everything basically. So namely, we start from the Riemann integration calculus that we build the so from the like the gluing along the like the branch cut to create the curved space Riemannian geometry. And then we know this naturally connects to a complex function theory or complex analysis. And this also naturally brings to the perspective the number theory and so on. So this mathematics is not for the like the even undergraduate or graduate. This is in general treated as a one of the like the very difficult like this subject. So that it is natural that with the like the hurdle of those like the difficulties, so one might not be easy to just sit to just start something. So I think that's not the from the like the laziness. More is about because it's highly non-trivial what to even start. And we are not just even talking about the how do we like the grasp the or like the knowledge from the Riemann surface theory. We would like to really understand the behind and the underlying like the ideas which should be also unclear. But I think this is also very worthwhile to like the try to keep digging this type of the unclear inspiration so that this could be eventually useful and helpful in the especially the situation that you feel completely like, ignorant but still you kind of get the experience and still what you can still try to do. So I personally believe that this type of the experience should be super useful for the further generations learning like the modern mathematics. But I still want to talk about the knowledge like the part so that one might be able to catch up. So here is the like the key theme that I think one should try to like the get track from the Riemann surface theory. So that I do believe that this like the theory. So the heart of the matter is the Riemann rule theorem, as we are at least like the philosophically agree with. And Riemann rule, like the theorem, is about the computing the Euler characteristic of the invertible shape coming from each of the divisor. So that we have the compact Riemann surface of genus tree and we fix the divisor. So even this like the second like the line of the sentence is very unclear for the beginner. What's the concept of divisor? Why we need to handle that? And how do we really like the establish those like necessary like the machineries? This is already highly non-trivial. And you all are just asking for the not just the naive definition, but the way of the like the usage and the philosophical pieces. This is very like natural to look at it in the like the advanced like the level. But anyhow, so we have a divisor, then determines the corresponding invertible shape. Then we are able to talk about the shape cohomology. We are able to talk about the Betti numbers. So the alternating like the sum of the Betti number or the Euler characteristic equals 1 minus g plus degree of d. That's the Riemann rule theorem. And you can easily say that, for example, this divisor contains either the tangent like the holomorphic line, holomorphic tangent like the bundle, holomorphic cotangent bundle. So that this also generalize the concept of the Gauss bonnet that when we compute the total curvature divided by 2 pi, that correspond to the 2 minus 2g. So this is also generalization for that. And at the same time, the in the like a computational perspective, Gauss bonnet does not concern over C. It concerns just over here. So that the key feature that we should like digest is that so if we compare with the Gauss one like the statement that we need to look at, so the one importance of the practicing the integral of the differential form is that we actually do not treat Gaussian curvature as a function by multiplying with the area form. So say KdA, right? So K is a Gaussian curvature as a function, and there's a square root of EG minus F square du which dV, which is coming from determinant whatsoever. So, or you are now kind of feel familiar with it. So that this, like the differential two form, KdA or curvature two form, was the major consideration from Gauss-Bonnet. And the surprising part was that this becomes the integer, and it's a very like a fruitful like the implication in terms of the Drunk homology and all those topological consideration, combinatorial like the perspective, and so on and so on. So that the primary like the computational focus is that how Riemann replace this like the computing the integral of the differential form as a component of the integration of the what differential two form over C. That's the key point. So that I want to just compare two perspectives. It should be still we have the real two surface, so that the integral should be taken with the differential two form. There's no other way to do around. But we just change the real two form for the curvature two form to get the now so-called the one form. One is with like without bar, the other should be with bar. So dz wedge dz bar, and the corresponding integrand is given by what? First chunkless. And this is coming from the exponential Schrodinger sequence. When we talk about the connecting homomorphism from H1 to H2, namely H1 of O star maps to H2 of Z. And this data of the H1 of O star is the collection of line bundle as a isomorphism classes. And this also naturally brings the idea of the divisors and also the invertible shift as well. So if I just summary, so the purpose is just to replace real differential two form as a complex one form. And then integrand like the data is coming from the collection of the line bundles up to the like the isomorphism, like the relation. And that also naturally gives the data of the divisors and the invertible shift. Then that also naturally like we should like go back that backward to understand those like the concepts in the with the computation as well. That's the kind of the big picture what we were aiming for. But for considering this like the cohomological like the description of the gluing the data globally, so that we know may arbitraries or the like the partition unity does not play a role any longer because of the holomorphic consideration. So that was the reason that we also needed to develop this highly non-trivial like language. But the one of the pros or the benefit was that so this way of the generalizing is that this forces it should be like the algebraic curve consideration as well. So that algebraic word is completely fit into this like the new framework of the ship cohomology, divisors, and so on. But we also at the same time know that this is coming from nothing but fundamental theorem calculus, because it's all about talking about the generalized Stokes theorem, truth be told. But we also know that as long as we can establish the interior with the boundary, then still we are able to apply the generalized Stokes theorem. Does not mean need to like the fix the like the field to be the real. So yeah, that's the major consideration, and each of the contexts really rely on what kind of the object you consider. Yeah, it's already long like the night. So if any of you have other comments or questions.
Yeah, my name is Byung-Ju Chun. Yes, I participated this enjoying math for about more 2 or 3 years. Mm, yes, already Professor an answered for the questions, and so my question is also I think my question is also repeated, but I just want to try to say something, anything. So I'm confused now, and I'm not confident if I can convey my words clearly. But so yes, my I why I in, want to study math and uh, participate this discussion is because I want to understand truly the elementary idea and elegant idea of about Riemann's yes Riemann's viewpoint. Yes, so and yes, so yes, from today's study, my question is yes, like simple. It's about invertible shift, and when from Google, Wikipedia, invertible shift is there is a definition of invertible shift, and there is very abstract language written in Wikipedia, and I just wonder how these uh, notation and symbols, abstract symbols, is corresponding to the concrete uh, uh, setting on uh, CP1 or cotangent bundle. Yes. So and there is yes corresponding between three object, different seeming different object, like it is line bundle, invertible shift, and divisor. But already Professor yes answered explain kindly. So I need to study and think more. Mm, yes.
So let me try to, but still give some like the perspective regarding these questions. So I don't think, including like the Byung-ju, the question is not just asking the like the just a line by line way of establishing correspondence, but more about the intuition and the way
Yes.
of
Yes.
the think and regard this like is the way to establish this correspondence. So then you need to just think about the original definition of each of the objects. So for example, when it comes to talk about the bundle, there are two major considerations. One is the local trivialization, as I told. So bundle is still just nothing but a certain topological space, if necessary, with the additional structure. When it comes to talk about the topological space, then there are only just two considerations. One is what is the type of the local neighborhood. Another one is how they overlap. Is a global structure. So either the global structure or local structure, that's all for the topological like consideration. And when it comes to talk about the bundle, it's the local structure, local trivialization. That's it. But the global structure does not mean we just look at the like the entire set or the ambient space. We need to describe the way to transfer from one to the other. Then that's the rule of the transition. So the one of the primary like the good example, all of you definitely know it, is the CP1 with the cotangent bundle. This is bundle. So that bundle, it can be described in terms of the local section, say DZ. And we know there are two like the local sections that 2 points that we should like the point out how to transfer from one to the other, from the South Pole to North Pole. And then that effect is now recorded with the data of the order of the like the pole or the order of the zero. So that's why we prefer to call the cotangent bundle as a so-called O of -2, because we fix the origin first from the complex plane, and then we just add the infinity, and then we just want to know how to transform from one to the other. Then we know dz is now transferred to the -1 over omega squared times d omega. I assume all of you understand what I'm talking about. So that the transferring data is the global data that we only care. And in the case of the CP1 or the two-dimensional sphere, we just know we can just cover them by taking just two open subsets, so that we just need to look at just this effect of how to change from this port to this port to the another port, right? So this is all about the understanding why the collection of the holomorphic line bundle furthermore becomes just nothing but just a Z, isomorphic to just a Z. That means the transferring effect will be just recorded in terms of the one point at the origin is transferred to the point at the infinity with just this like the information of the order. Just that's it. And one just need to see why it is really enough to really see just this data. That's the only maybe consideration we need to care. But so it's also important that there is an effect of the taking quotient by the principal divisor. And that's the reason that even though there are several like the points, we can actually move all points to just one point with that reason. So that now you can use the definition to see, but the intuition is how do we like the record this like the global data in terms of the transition from one to the other, just the same. And vice versa. So you can just look at each of the objects so you need to look at the definition first. And then from the definition, you need to think about the desire. And then with the concrete example, if the desire clicks match with the concrete like the observation, then you can kind of get more gain the confidence, and then you can just do back and forth to figure out what was going on. Then that's the way to figure out the proof. I think this type of the explanation should be the answer.
I got it.
Yeah. Any other comments?
I have questions about vector space called the Riemann law space. I get that from divisor, we can define a Riemann law space, which is a vector space of manifold functions constrained by divisor. But beyond the fact that it's a vector space, I'm still wondering why we think about this vector space.
It's a little bit like a tricky, truth be told. So, of course, Riemann root theorem has indeed like the millions of applications. So I don't want to like the list all those like the context for sure. But the one of the primary related usage is so I want to talk about the more like the algebraic like the nature for that. So the in order to obtain this algebraic nature, then one need to consider the embedding. Then in order to find the embedding to the projective space, then not just looking at the form, but we want to look at the function. But the one of the defect of the Riemann rule is this states dimension of the LD minus dimension of ID equals something. So that we really want, so your question, one of the question, the primary question right now is the why do we care the dimension of the LD? Then I instead wanna like the talking the like the answer, I'd like to say, so by taking this certain divisor, let me just give it a very concrete like the answer. If you take the divisor to be just take any point P and just multiply by the integer, say G plus one, G is the like the genus of that like the Riemann surface. Then if you take that divisor, then you can see that if you plug in this divisor G plus one times P into I, then you can see that this I must be the zero dimensional vector space. This is also one of the like the application of the Riemann rule as well, and you are able to find this like the proof from probably like the ninth note of my like the note I post. So I of like the D in this case would be just the dimension is now zero. So now we can kill so that dimension of the LD is now equal to something. So now you can like quantitatively like to really count this dimension. Then once we count this dimension, then we can exactly try to collect those like the metamorphic functions. Then with that metamorphic functions, we might be able to embed to the projective space with the exact numbers of the bases. So it's really about whether or not. So first, so with many reasons, we'd like to find the rational functions with many reasons, right? Right. So this rational function is now just a the translate as just nothing but a matter function on the computer Riemann surface, so that we just want to know how many of them. That's the information of the dimension of the LD. But in order to know that data, then we first need to know the dimension of LD. That's the spirit of the Riemann rule. But in order to do it, we want to even kill the information of ID. Then once we know this vector space, then for example, it guarantees the existence, first of all, right? And then so once we find them, then we might be able to use that for our application. So the L of the primary application is that so L of so if dimension is n, then this becomes C vector space. So C isomorphic, there's a vector space isomorphic to Cn. Then if we projectivize, then we have this Cpn minus one. Then this guarantees the embedding from the Godira embedding. So I always tell a little bit lie in this context that I always said, given compact Riemann surface, then once we embed to the CPN, then it becomes the algebraic curve. So the context of the telling a lie is that this is actually not exactly CPN. The reality is the following. Because if you just find the arbitrary embedding, how do we really guarantee this becomes algebraic curve? That does not make sense. So the way to do is we find a certain divisor whose I of D is zero, first of all. This is I always skip to say. So we first find the divisor D whose I of D is zero dimensional. Then we can exactly count the dimension of LD. Then we know this as a C vector space. Then we projectivize. This is actually a real answer of the complex projective space. I always just skip. Then just because we know the basis of these metamorphic functions, then we can naturally we can usually define the map to the like the CP n minus one, where n is the basis of this LD. Now we should use this data. Then with this specific map, with just filling each of the components of n tuples by just metamorphic like the function basis, then one can argue that first of all, this becomes embedding, meaning that this is one-to-one, and this is so-called the emergent, topologically speaking. And So, and by using this like the algebraic data, one can also show that this indeed satisfy all algebraic like the relation, zero sum of the polynomial like the polynomials. So it's a like it's this algebraic extension one should be able to argue by using the complex Riemann surface data. Then that gives the embedding. So for example, this is more primary usage. So that for like the algebraic geometry coding theory, for example, one is taking caring of the Riemann row, like the space, for example, LD. What's the main purpose? We want to find embedding. Why we want to find embedding? Once we find that embedding with the specific dimension, then we are able to find the corresponding algebraic relation because we know the dimension of the curve. We know the numbers of bases that determines from the rank nullity like perspective that determines numbers of the algebraic relations that we are looking for how to describe. So that's one primary like usage that you might care. Yeah, probably Inho, you might speak something if you have anything, then we might stop the record.
Okay, hello, I'm Inoso, and I have a question about the bundle on complex Riemann surface. On CP1, any divisor degree 0 is become a principal divisor, but at higher genus surface like torus, we need a special setting like Weierstrass sigma function to require to be a principal divisor. So I want to ask these kind of uh, difference would change the characteristic of vector bundle on CP1 and torus, and does it make any difference about the vector bundles uh, characteristics on those CP1 and higher genus surface?
So let me just say address the context more like the geometry and physics context. I'd like to say. Um, So not just the talking about the comparison of the each of the specific like the structures that we might be able to compare for each of the complementary surface of genus G. But yeah, what you said is completely correct. So for CP1, because the genus is zero, so our principal divisor is same as the class divisor group, for example, it's just a zero. So that's definitely correct. But so one primary focus of the considering the divisor in that context is so from the Jacobi's perspective, so Jacobian of the complex Riemann surface, the goal is to transfer each of the complex Riemann surface which has a lack of the symmetry to the torus of complex dimension G whose symmetry is very well understood in terms of the lattice structure. So one consideration from genus greater or equal to one is that so that if we collect the degree zero divisors up to the principal divisor, then that collection becomes the complex dimension G torus. And the important like the desire behind is that it's hard to talk about the symmetry of the given complex Riemann surface, but when it comes to transfer to the data of the torus, then we can easily figure it out the data of the lattice then we are able to say something. This is the key feature of the also the Riemann's hypothesis, for example, in a way that Riemann's hypothesis concerns the prime distributions from the zeta function, for example. Then in the like the era of the Riemann, he knew from the Euler's like the contribution how to rewrite the zeta function as a infinite product over each of the prime as a so-called like the prime the factorization for the zeta function. But over then this is with the analytic continuation, this is just the entire function. There's a metamorphic function defined on the complex plane. But so what? We have no idea what to do. Then what Riemann did is that so from the Jacobian of the Riemann surface, then we can transfer this space, this topological space that we do not know how to handle to the case of the torus so that the corresponding zeta function should be transferred accordingly to the torus. That is the so-called zeta function is transferred to so-called the theta function. And the way to transfer from the zeta function to theta function is that, so Riemann knew the mathematics of Gauss for sure, and also he knew the mathematics of the Euler, and Euler considered the gamma function as whose integrand is given by ln of the power. So that's the one of the equivalent form of the gamma function. And if you look at the expression of the gamma function, that also contains the data of the zeta function. So that is now like the translated so-called Mellin transform. And if you apply the Mellin transform to the, if I tell not lie, the so-called not just a original zeta function, but so-called a completed zeta function, that would be converted to the so-called theta function. And theta function is the like the generator of the metamorphic function field on the torus. So at the same time, theta function is double periodic because it's defined on the torus. And at the same time, this is a solution of the heat equation, so that it has a large, more like the symmetry, and there's a way to do around. And this established the Riemann hypothesis. If you just look at the theta function, and if one take the inverse Mellin transform, one can go back. So the one of the primary the desire of the geometry is we'd like to know the symmetry of the underlying space. But if the underlying space doesn't has a lack of the symmetry, then we want to transfer. Then one of the the good usage of the symmetry is in the case of the torus. So that we want to just so is Riemann establish the way to the transfer the data to the data of the torus, then we can do something. That's the one the important the nature. But at the same time, I also want to put more context, because I know you are doing research or studying in physics. So one the lack of the Riemann's the theory in 19th century is that the perspective is actually a little bit wrong, I should say. So compact Riemann surface is an algebraic curve. Already says we start from the topological space. We start from topological states, so that we can even regard it as treat as a manifold, or we can treat it as a so-called algebraic variety. Or more generally, from the mathematics in 20th century, we might treat it as a so-called scheme. But actually, none of them works properly in this the context, in a sense that, for example, collection of the torus, or even collection of collection of, for example, one-dimensional torus, is not neither of those structures. It's actually beyond those structures, so-called either the orbifold or stack. And the data is actually beyond what we described in the following sense. So in the even 20th century, what mathematicians believed was that we start from the set, then we have a power set, and if power sets the sub collection satisfy blah blah blah, we want to put it by as a topology. And with the additional structure, either the smooth structure or the algebraic structure, we can talk about the manifold, we can talk about the algebraic variety, we can talk about the scheme. But the very the first line is already wrong, because we start from the set. And if you look at the certain collection, we from the the logic or the elementary set theory, we know set isn't good enough to collect the meaningful pieces. The collection of a set is no longer the set. We learned that, so that this very first line could be wrong. So the, for example, collection of the torus is no longer the set. Truth be told, I never actually tell this a lot in this context, so that it's already wrong from the beginning. So that one need to extend this context more like a categorical perspective to really see the additional the structure. So if you want to search, then you can search probably moduli stack of the elliptic curve. Then of course one can just view this as a complex the manifold, but this lose the very important the structure already. So even in the algebraic geometry, aiming for studying the mathematical physics, so manifold, algebraic variety, algebraic scheme fails because there's an additional structure, and that structure is we should surpass the structure of the set. So that we should topologize category. We should also give the way how to do the differentiation and integration in terms of the homological algebra, and so on. So the more physical context that I personally think what you care could be actually beyond that we are now talking from this study group, and also the beauty of algebra, truth be told. But in order to first do it, one first to establish the very clear understanding of the compact Riemann surface and the algebraic curve, and what is actually the defect. And let me just summarize this way. If one look at just the DZ on the compact torus, and equivalent to speaking, if one look at the elliptic curve equation, y squared equals x cubed plus ax plus b, then the corresponding dz becomes dx over y. Then if one just look at just one like the object of the differential form defined on one topological space, no issue. But if you collect all of them, this is no longer the set. There's additional structure so that it like, just beyond the set, so that one should like the develop this like a language. So this like the field is more like a mathematical field is more like the homotopy type theory, like the area, in my opinion, and it's more like the stacky like the perspective or mirror symmetry like the perspective. This is a different story. So the structure you might like the look for eventually could be different. This is also one like the like the perspective I'd like to put. So you can, for example, look at the some. You can just search from the Google. So there should be like the some articles in the elementary like the approach that so the like the homological mirror symmetry of the elliptic curve. Then there's a so-called A side and also B side, and it's more like a category like a perspective. One of the key reasons is that it should actually be on this like the structure of the manifold or the algebraic like particular scheme. So this is the one comment I'd like to put from the like the message you previously just sent to me. So this is what I also want to share. All right, so this is like the like the record. So it's like already like the after the 1 a.m. in South Korea. So yeah, thank you very much for like the participating this like the conversation. And I will just post like this like the record like a video to the like the especially graduate student of the Texas State, so that during from this summer, if you are willing to talk with them, this you are able to do it. And uh, trust me, they might give some gossip on my lecture because I gave in this super compact contents that you have learned more than half year, right? So that I needed to do back and forth with like skipping so many important like the details, so that there should be the way to support each other. But I think this could be eventually good for all of us. So let me stop to record.